Good morning to all of you.
Good morning, sir.
Do you remember where we had stopped? Because we are meeting on internet, although we are unable to see each other. Probably you are looking me. Where we had stopped. With respect to doubly reinforced, probably the theoretical part we had completed and tried to solve a numerical problem. Now see this, here is a problem. It is not difficult. See, a reinforced concrete beam having effective section 250 by 450 is reinforced by 420 mm Tor bar. This represents 4 is number, 20 is diameter as tension steel, and 3 numbers, 12 Tor bar as compression steel. The compression steel being at an effective cover of 50 mm. If M20 concrete and M15 415 steel is used, determine the ultimate moment of resistance of the section. Now see the peculiarity of the problem. You are given effective section. So you are given effective section means you are given width of the beam section and depth of the beam section. It is not giving the overall depth. Effective depth. So effective depth we have defined in our single reinforced section. It is depth from extreme compression surface to centroid of tensile steel, right? So this 250 is the width, 450 is the effective depth. So see in the sketch. See in the sketch. The sketch is just schematic sketch. Okay. So here D is given. So see here, D is centroidal of the tension steel. And DC is given. Effective depth of compression steel. In our single reinforced section, this did not arise. So this is given 50 millimeter. Normally 50 millimeter is adopted as effective cover if any environmental condition is not mentioned. Grade of concrete is given. Grade of steel is given. Okay, it is not. So here you see it is schematic drawing. The schematic drawing. Okay, this is this section. This is the section, and this is the strain diagram, and this is the stress diagram. This is the stress diagram. And any solution of the problem will require these three diagrams. So this amount of compression steel. This amount of, are you able to see the mouse? Movement of the mouse? Are you able to see? So this is our compression steel and this is our tension steel. Okay. Here it is 4 numbers 20 mm, 4 numbers 20 mm, 3 numbers. Okay, so total amount of compression steel and total amount of tension steel is 2. Now here you see I am calculating area of steel, AST, area of steel. AST represents area of steel in tension. A area, S steel, T tension. This 4, the cross-sectional area of 20 mm diameter is 314. So this ASC, A area, S steel, C is compression. So 313. Okay, so this is known to us. Okay. Now the critical neutral axis depth. Since our grade of concrete is 415, this we had already obtained. XU by X critical by D is equal to 0.48. So, okay, so this we had so XU maximum is 0.48 D 230, 216. Now we will be required the actual neutral axis state. So how to calculate neutral axis state and what are the information we are having. So this diagram adopted, we are to find out the CUS, total compression, ultimate compression in compression steel. CUC, ultimate compression in concrete, and C is equal to CU plus CU is equal to CUS plus CUT. These expressions we have obtained. Now let XU actual neutral axis state. Okay, again we are considering that stress in compression steel and stress in compression steel attains the same value. So, see, we are assuming this part we had adopted in our previous calculation also. FST is equal to 0.87 Fy in single input section. Now we don't know what is the stress in compression steel. So at the beginning, we assume that stress in compression steel as well as stress in tension steel are same. If not, it will our solution, continuous solution, it will give our indication. So this is 0.47 into okay. Now this expression we had already obtained. CUC is equal to 0.36 BXU FCK. So 0.36, B is 250, X is unknown. We are going to find out. FCK, characteristic compressive stress. So it is 1800 XU. Okay. Now CUS still. Now here this expression also we have got FSC minus 0.44 CK ASC. Now this part, this part this part 0.446 this part 0.447 FCK 0.447 FCK. That means at this location if we at this location originally concrete was there, now concrete is not there, so that's why the concrete sense has been deducted. But the value compared to here again you come compared to FSC, we don't know until now, we just adopted. We just assume, not adopted. Compared to FSC, this value is very small. This value is very small. So in our future course, we will neglect this part. We will neglect this part. Now here, since it is beginning, we have to solve whatever expressions we had got. So this FSC is equal to, see here we have assumed FSC is equal to FS is 361. So 361.47 into 20 into ASC. ASC is given to us. ASC is given to us. So 339 is given, so we got this, right? Very simple. Very simple. Okay, so total compression is equal to, so here the unknown remains XQ, actual neutral axis state. Okay, then how will to find out? So XU, then find out the total compression. So total compression, this expression we had utilized in our single reinforced, same to 0.87 FYAST. So this is this one. Now for equilibrium, there should not be any unbalanced horizontal force, or there should not be any unbalanced axial force on the beam. So total compression must be equal to total tension. So this we had adopted, we had these expressions, with this expression we had got this is this is our total compression left hand side and right hand side. From this we will get XU is equal to 186. XU, actual neutral axis depth is 186 and critical neutral axis depth is 260. So we are on safer side. We are on safer side. The critical neutral axis depth is higher than actual neutral axis. But the question is coming, whatever critical neutral axis depth we had calculated, it is correct because it is dependent only on material property and the effective depth. Only on material property of the effective depth. It has no any link with external load. It has no any link with external load. It is constant. But actual neutral axis is dependent on external load also. Dependent on external load also. So this may not be correct. Then now we'll have to check it whether our actual neutral axis test is correct or wrong. So here, see, argument. Now we are coming argument. So XU is the assumption FST is equal to 0.87Y is correct. Here we FST is equal to 0.87 Fy. Since actual neutral axis depth is less than critical neutral axis depth, then our consideration stress in steel in tension zone is equal to 0.87 Fy. It is correct. Now we have to check whether stress in steel in compression zone also attains the value 0.87 Fy. That is yes or no, that we have to establish. So we will have to establish by trial and error method. Okay, how we will find out? So epsilon SC strain in steel in compression, so is equal to this expression you will get from these two similar triangles, this one triangle and this another triangle. So this is very simple, 0.0035 0.0035 minus 1 minus dc by xu. Okay, so this u 50, it is already given, right? 0.002. What we got? Strain in steel in compression zone, right? Now we have to find out the strain in steel in tension zone. So strain in tension zone is this expression, whether I had given it or not. This is the expression. 0.87 Fy by Es plus 0.002. Now come here. 0.87 Fy divided by E. Point plus 0.002, 0.0038. Now, strain in steel in compression zone 0.0026. Strain in steel in tension zone is 0.003. Strain in both the steel are not same. Strain in both the steel are not 7. Okay. If it is not correct, strain in steel, both in compression steel and tensile steel, are not same or equal, then we can very simply we can say that stress in steel, both compression steel and tensile steel, will not be equal. Stress in steel in compression zone as well as in steel in tensile steel is not equal, right? Now, strain in steel in strain in steel in tension zone is more than strain in steel in compression zone. Okay, so strain means there is deformation is less. So if deformation is less, that means apply induced force is less. That means stress in steel in compression zone will be less than stays in tension zone. So this is the thing. So that means say FSC is not equal to 0.87 FY. Then what? How we will find it? Now we'll have to go trial and error method. Okay, so correction. Let us assume that epsilon SC is equal to 0.002. So FSC is equal to 0.8786 FY. Now where from we will get this? Where from we will get this? So this we are getting. There are two ways. One is I have gave you one table. Another is now this table will not be available in your examination because this is not available in IS 456. This is available in SP16. Your SP16 will not be given to you in your examination. When you are going to solve practical problem, under that situation, you will be able to utilize this table. Okay, since it is not, since now your student, it is not given, so we have to utilize the actual procedure. So actual procedure now, this FSC is equal to 0.86. FSC is equal to 0.86. Now, where from we got this? Where from we got this? So this we will be able to find out from a graphical representation given in IS 456. When in IS 456, where I cannot give the clause number, I forgot it, and the code is also not available to me. So when in the chapter design limit state design, there is a chapter limit state design. So there are three terms. One is with respect to steel, one is with respect to concrete, and another is with respect to cold deformed steel. Okay, so that's hot deformed steel. So that is a peculiar curve. Stress by strain. Stress is horizontally, strain is horizontally, stress is vertically. Up to some point it is strain, and then it is curvature. Okay, so from this we will be able to find out the stress. So our stress is first epsilon SC is 0.002. So you look at strain 0.002 on abscissa, go parallel to the straight line, it will reach the curved line. So at that point, you go horizontally to the abscissa, you will get there 0.86 FY. It is very, what I should say, you close observation will be required. Whether it is 0.86, 0.85, it is your own visual capability. Okay, so FSC, a new FSC we got. You need a new FSC, we got 357. Now, go back to your original expression. So again, so therefore, FSC, this expression, this, we got this. And CU is this, and from this we are getting XU is equal to 186.38. So previously we had got 186. And first we had got 186. Now it is slightly increased, 186.3. Now whether this value is correct or not, where we require another cycle. First we had got the second cycle will dictate you. The second cycle will dictate you which one is the correct actual neutral axis step. Now again, same procedure, but you see in second cycle again epsilon SC, this value, this is dictating. Now you see it is almost same value, 0.0026, previous also 0.0026. So the same value it is coming. That means it is correct. So now this part is with respect to conversion, concrete, and this part with respect to compression steel, CUC D minus 0.42 XU. Expression we had utilized when we had done our single reinforced section. Now this is with respect to CUC into D minus DC. CUS, it is acting on these things. So we require a lever arm. Lever arm is from here to here. So from here to here, it is effective depth minus effective cover for compression. So effective cover for compression. So 1800. This we had got XU D minus XU CUC into yes. So 1800 into 186.38 into 450 minus 0.42 186. Ultimately we had got this much kilonewton. This much kilonewton meter. Okay. Now this second method, it is just application of those that table. In the application of that table. Okay, it is very simple. It is very simple. It is very simple. You see, B, D, DC, this is 10 things, and critical neutral axis that remain same. DC by D ratio. DC by D, it is ratio. Compression steel to actual effective depth, so it is 0.11. So DC by D is 0.1. Now go to that table. So this table will not be available. So this 0.1. Now see, the tables are given 0.05 with respect to 0.05, 0.1, 0.1, 0.2, right? With respect to, so we are with respect to this line. Now DC by D is 0.1. So our value is 353. Value is 353. FSC is 353. Now you see here. FSC, mistake. 0.1. I'm writing 342. I'm writing 412. Somehow 342. It should have been I had written with respect to 0.15. I had written with respect to 0.15. Now, why I had written 0.15? All of you are listening? All of you are listening?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
You see here, I should have written FSC FSC 353. I had taken 342. Do you feel I made mistake? Anyone? In place of 353, in solution of the problem, I have taken 342. Do you feel it is a mistake? Anyone? Anyone? You are not hearing me? Okay, I'm giving the answer. Now, why I have taken 342 is less than 353. I have taken stress induced less than 342. Now, what happening? Taking 342, what happening? Taking 342. What FSC I have taken 342, right? So 0.36 FCKB into XU, FSC, ASC, and FY neglecting the value. Yeah, we had neglected it here. Okay. Now, from these expressions, we are trying to find out. We are trying to find out the value of XU. We are trying to find out the value of XU. So we had got X is equal to 187.5. X is equal to 187.5. Why this happens? Now in our previous solution, we had got 186.38. In this solution, we had got 187.5. What is this difference? What is this difference? The neutral axis, actual neutral axis happens to be more than our previous solution. Why this happens? Why when actual effective depth will be more? Now that is the cause. That is the cause. Now see here, FSC times ASC. This part was actually FSC times minus 0.447 FCK. That's what we had neglected. So this value of this part we had increased. Value of this part we had increased. So since we have increased the value of this, because of this value of increase of this, value of increase, so this going to be less. Okay. Now this part we had not checked in our previous part. That there also we can say, since XU is less than XU, it is under reinforced. That means reinforcement we are providing less than whatever required with respect to balance. Okay, so moment of resistance we have to calculate with respect to compression zone. So 0.86, 0.36 FCK, this FSC, ASC, So this ultimately we had got 171.62. With our previous solutions, we had got 172. It is 171.62, almost equal by both the method. Okay. Hmm? Huh? This correction. Okay. Okay. Effective section 251 depends on and 416 as compared on the same problem. Same problem. What is going to happen if we increase the amount of step? Going to utilize 4 number 25 thought and 3 number 4 number 16. Now what differences are we? Remember, cross section remains same. Cross section remains same. Now because of this, what is happening? Let us see, and at the last lead, let us count. Now see, the moment of resistance had been increased. In our previous problem, moment of resistance was 172. Now in this case, our moment of resistance is 258. The procedure is same. I think you will be able to go through it. Yes. Yes. See, probably there is one more problem. No, there is no problem. Okay, there is no problem. Only I have given this two problems, not difficult. Only thing that it is slightly tedious. It is slightly tedious. It is slightly tedious, but after able to find out, you will be able to find out how to design double reinforced action using some table available in SP16. Also, those tables are reprinted in your RCC book. So how we'll be able to find out? I will just dictate you. There are some table and there are some curve. So we know this MU. Let us say we know this MU. If we are to find out this amount of steel required. So this problem I have not taken. Next time I will give one problem how to find out the amount of steel. Oh no, the amount of steel required we had solved. The amount of steel required we had solved previously. Say. So by using our tables, it's very simple. If we are to find out the area of steel required, moment is given. So we have to find out the one constant mu divided by bd square. Mu divided by bd square. Now in that table you will get just like this FE 250, FE 415, and FE 500. So for all these tables are there. You consider the concrete. You consider grade of steel just like this. So what you find out mu by BD square is known to. Go to the in the vertical curve mu by BD square. It will mu by BD square. You find out DC by DC, D by DC by T. Taking help of this, you will be able to find out a percentage P. P you will get PT and PC. PT means percentage of steel required in tension zone. C means percentage. So by that way, we'll be able to find out it. Okay. Hmm? Next time we'll try to solve. Next time we'll try to solve a full